Hello everyone, welcome back to Tales of Chemistry. Today we are going to start a new lesson which is chemical kinetics. So as the word indicates, kinetics. So this is something which is relating the speed of the reaction or rate of the reaction and mechanism of the reaction. So from the word itself, it is clear that chemical kinetics is the branch of chemistry which deals with the study of chemical reactions along with the mechanism of the reaction. So, study of rate of reaction along with the mechanism of the reaction, that is called chemical kinetics. Now, the chemical reactions are mainly classified into these three types. One, very fast reaction or instantaneous reaction. They're very fast reactions. Before even you could realize the reaction is over. Say, for example, the salt analysis, what we do in the lab, most of the salt analysis reactions, say, for example, when you take chloride, okay, and say sodium chloride or any chloride solution in a test tube, and you are adding HNO3, AgNO3 mixture into it. By the time AgNO3 is added, just on the sides of the test tube itself, you can see that white precipitate of AgCl. Before you could even complete the addition of AgNO3, you are getting to see the result of the reaction. So they are very fast reactions. Then we have very slow reactions also. Rusting of iron, right? So rusting of iron takes days together or months together to complete. Most of our reactions are moderately paced reactions. Speed of the reaction is not very fast and it is not very slow also. Most of the reactions, all of our organic analysis, all those are examples for moderate reactions. Every organic chemistry experiment that you do in the lab, they are examples for moderately paced reactions. Hydrolysis of ester, decomposition of hydrogen peroxide also is a moderately paced reaction. Okay, so now here rate of a reaction. So the next topic that we need to discuss is rate of a reaction. Rate of a reaction can be defined as the change in concentration of any one of the reactants, change in concentration of any one of the reactants or change in concentration of any one of the products per unit time. Okay, may sound something difficult to understand, right? So, rate of a reaction. Let us analyze this, bit by bit, part by part. Rate of a reaction can be defined as the change in concentration of any one of the reactants. So they mean to say that when the reaction proceeds, the concentration of reactants are decreasing. At the same time, concentration of products are increasing. So, if you consider a hypothetical reaction, R gets converted to P. R gets P. I used a R to indicate a reactant and P to indicate the product. Now, rate of this reaction is change in concentration of any one of the reactant. So, there is this reactant R. Suppose initially I have taken R1 and after some time there remains R2. Okay, so final concentration is actually R2 minus R1 and the time taken for the change is delta T. Okay, here just because the concentration of reactant is decreasing, okay, R2 is definitely lesser than R1. So, we write it as rate is equal to minus delta R, that is change in concentration of R minus delta R by delta T. So this minus sign here indicates that the concentration of the reactant is continuously decreasing. So the same rate can also be expressed in terms of product. So I've taken P here for product. Initially, let me take, there is P1 of the product formed. After some time, there is P2. So final, that is P2 concentration minus initial concentration, that is P1, time required for that change. Look at the last part of the statement. Per unit time. So whatever is the change in concentration, that has to be divided by the time taken for that change. Now, this is equal to delta P by delta T. So, whenever you express the concentration in terms of the reactant, you must be writing this minus sign, okay, because the concentration of reactant is decreasing gradually, and for in terms of product there is a plus sign. Plus sign you can skip, delta P by delta T. So that is the meaning of this term rate. Okay, now the bracket around the R and P, which I have put here, that has to be a square bracket. You cannot put any other, bracket here, because the square bracket has got a meaning. It stands for molar concentration. Yeah, the square bracket represents the concentration of the reactant or the product in moles per liter, molar concentration. Well, now, the rate of a reaction can be expressed in two different ways. One is average rate of reaction. Other one is instantaneous rate of a reaction. Now, average rate of a reaction is when you have, when you are calculating the change in concentration of either the reactant or the product, but over a period of time, say in 30 minutes, this is the change, or say in 15 minutes, this is the change. Yeah, in the concentration of product or the concentration of reactant. So you're keeping a little larger time interval. Then, in such cases, the rate which is written is called average rate of the reaction. Okay, average rate of reaction. When the rate of a reaction is calculated for a certain interval of time, with change in concentration of reactants or product, is called the average rate. Now, This is not a very ideal method of calculating the rate. I said this is not the best method to calculate the rate of the reaction, just because the time span is too long, too large. You're keeping 30 minutes or 20 minutes or say 15 minutes of time to check the change in concentration of product. In that 20-minute itself, you know, the rate can change, the speed of the reaction can change. I mean to say, in that 10, 15, 20 minutes of gap time interval which you have kept, the rate of the reaction is not uniform. The rate of a reaction keeps changing. So in that 10 minutes time or in that 15 minutes time also, rate keeps on changing. All right. But average rate, this is the definition. Rate of reaction is calculated for a certain interval of time with change in concentration of reactants or products is called average rate of a reaction. So whatever we have studied in the previous slide here, the delta R by delta T or delta P by delta T, that itself is average rate of a reaction. Now, the most accurate way of expressing the rate of a reaction is the instantaneous rate. As the term indicates, instantaneous rate is at this moment. Okay, at this moment, this is the rate of the reaction. Yeah, after this moment, the rate will be something different. Before this moment, the rate was something different. But at this moment, that is the meaning of instantaneous rate of the reaction. At this particular moment, this is the rate of the reaction. So, instantaneous rate of reaction is defined as the rate of change in concentration of any one of the reactants or products at a particular instant of time. Any one of reactants or products at a particular instant of time. So the main difference between average rate of a reaction and instantaneous rate is average rate is calculated over a interval of time, a particular duration of time, whereas instantaneous rate is calculated for a particular moment. The expression also here, we are using d by dt of r minus d by dt of r and plus d by dt of the concentration of products. R in square bracket represents the change in concentration of reactant and P in square bracket change in concentration of the product. So I hope the difference between average and instantaneous rate is clear. This itself can be taken as a question. What is the difference between average and instantaneous rate of a reaction? Now, let's understand how do we graphically represent the average and instantaneous rate of a reaction. Graphical representation. Okay, so both the average and instantaneous is done in the same graph. So the first graph here is concentration of reactants plotted against time. Okay, so the curve tells us that as time proceeds, concentration of reactant is decreasing. So here, let me take this as R0 or R0, whereas this R0 is the initial concentration. Now, to calculate average rate, okay, I am waiting for a time gap between T2 and T1, so a particular time interval. So let us analyze what I have already written here. So this particular point, I've called it R1. What is the meaning? the concentration of reactant is now R1. Now, after some time, say 10 minutes, after some time, I'm checking the concentration of the reactant again. From R1, it has come to R2. Okay. At what time the concentration of reactant is R1? At time T1. And at what time the concentration of reactant is R2? At time T2. Okay, so what is the formula to calculate average rate? The final concentration, that is R2, minus initial concentration, that is R1 here, and the time taken for that change, which is T2 minus T1. So here R2 minus R1 is what I've written as minus delta R, because the concentration is decreasing. R2 is lesser than R1. So minus delta R, and the time required for this change is delta T. Okay, now instantaneous rate. So I've just written or marked one point here. At this moment, what is the rate of the reaction? So to calculate that, what I have done is, we need to draw a tangent to this point. Yeah, we need to draw a tangent to this point and find out the slope of the tangent. So the red line which I have drawn first, that stands for the tangent, and then find out the slope of the line. So now if this little bit, this tiny part here, that represents change in concentration of the reactant, and this represents the time required for that change, then our instantaneous rate of reaction or instantaneous rate of reaction is minus, because the concentration is decreasing, minus dr by dt, which happens to be the slope of the tangent also. Okay. Now, same thing we can repeat with respect to this product. This curve is of this shape because concentration of products are increasing. As time proceeds, concentration of the products are increasing. Suppose initial concentration P0, initially there will be no product. As time proceeds, at time T1, P1 is the concentration of the product. At time T2, P2 is the concentration of the product. So our average is equal to P2 minus P1 divided by the time taken, T2 minus T1, which is delta P by delta T. So this does not require any explanation, right? Similarly, instantaneous rate. So I've marked a point here. Next is to draw a tangent to the point. So let this be the tangent and then find the slope. Okay, find the slope. This part is delta T and this is delta or dP, change in small change in concentration of product, small change in time taken. So R instantaneous is equal to d by dt of product, change in concentration of product with respect to time, d by dt of P, change in concentration of product with respect to time. Yeah, generally a graph is not asked in ISC board examination. This was just for your information. Okay, now moving forward. Dependence of relative rate of reaction on coefficients in the reaction. Now, the previous examples which I had taken, that is R gives product, yeah, it was actually taken, with a purpose, like 1 mole of R gives 1 mole of P, something like PCl5 decomposes to give you PCl3 plus Cl2. All right. So the coefficient, the stoichiometric coefficient, the number in front of each of the term, that was just 1 in all the cases. Now, all our reactions are not of that type, correct? Now, this is one example for the similar reaction. 1 mole of something decomposes to give 1 mole each of two products. SO2Cl2 is giving you SO2 plus Cl2. Sulfuryl chloride is giving you sulfur dioxide and chlorine. Simple reaction. So here, the rate of reaction is delta SO2Cl2, change in concentration of SO2Cl2. Since it is the reactant, we should put the minus sign by the time taken for the change, which is equal to d by delta SO2 by delta T, or delta Cl2 by delta T. So that was average rate, which I have written, represented here. If it is instantaneous, you just have to write d by dt of the same thing. Now, the problem is not all reactions are that simple. Look at this. 2N2O5 gives you 4NO2 plus O2. So the coefficients on, the reactant as well as the product is not equal to 1. 2 moles of N2O5 is reacting to give you 4 moles of NO2 and 1 mole of O2. So with respect to O2, it is our same method of representation. That is plus because it is the product, delta concentration of O2 by delta T. Whereas wherever the coefficient is not equal to 1, we need to divide the rate term. Okay, we need to divide it by that number. So since I have 2N2O5 here, okay, rate of this reaction is minus 1 by 2 delta. So that 1 by 2 minus is because it is the reactant. Since 2 is the coefficient, here I'm dividing, the term by 2. So 1 by 2 of delta, change in concentration, of N2O5 by delta T, time required for the change. So here again, 4NO2 is there. So normally you write your rate term, but divide it by the number, the stoichiometric coefficient. Here it is 4. So divide it by 4. Okay, so this will happen whenever your, equation for the balanced equation is not a simple one. You have multiple reactants and a different number of moles of products are formed. Now, let us move on to factors affecting the rate of a chemical reaction. This question was asked many times before. This is generally a 2-mark question where you need to write 4 factors which affect the rate of the reaction, or it can come for 1 mark where you will write any 2 factors that affect the rate of the reaction. Okay, so now the factors which affect the rate, speed of a chemical reaction. One is nature of reactants. Now, what I can take or tell you here is, our chemistry lab experience can be used here. Some of the reactions are very quick. In the beginning of this session, I told you AgNO3 when added to a sodium chloride solution, right? Before you finish the addition of AgNO3, you get to see the result, which means that reaction is very fast. Why was it fast? Because the contents of the test tube, NaCl solution, NaCl is ionic in nature. Already that NaCl is existing as Na plus and Cl minus ions. And what you have added, AgNO3, even that is Ag plus NO3 minus, or even, since it is ionic reaction, it is a faster reaction, whereas organic reactions are taking time. Why are organic reactions taking time? Organic reactants are covalent compounds, so they need time to break the covalent bond and then get into a reaction or form something new. So here in ionic reactions, it was a very simple mutual exchange of ions, whereas covalent reactions, you needed to give it some time to break the existing bond, react to form new product. Concentration of reactant. So this is very simple. The more the number of moles of reactants that you have taken, more will be the rate of the reaction. More concentration simply means the number of collision between the reactants are more. The interaction between the reactants are more, and as the interaction between the reactant increases, speed of the reaction will also increase. Third one, temperature. So in most of the cases, okay, as the temperature increases, speed of the reaction, rate of the reaction also increases. Now, it is observed that it's an experimental fact that for every 10-degree rise in temperature, for every 10-degree rise in temperature, the rate of the reaction either doubles or triples. Rate becomes twice or 3 times for every 10-degree rise in temperature. The fourth point is surface area of the reactant. So again, you can easily understand this. Yeah, if you try dissolving some sugar crystals in water, okay, it will take some time. At the same time, you powder the sugar. Yeah, in a mixer, you powder the sugar, and then you try dissolving it in water. In no time, that sugar will be dissolved in water. Now, what is the difference? When you powder, the surface area is increasing. So, more the surface area of the reactant, easier it is to dissolve or easier it is to react. Now, fifth point, we are very much familiar with. A catalyst definitely increases. Okay, by definition, catalyst can increase or decrease. There are positive as well as there are negative catalyst. All right. So, if we take a positive catalyst, the rate of the reaction is increased by a positive catalyst, and rate of reaction decreases by a negative catalyst. Last point is radiation. Radiation as in, there are certain reactions which are photosensitive. Photochemical reactions are there. Now, if you keep a silver compound under direct sunlight, in no time it will be decomposed. Hydrogen combines with chlorine in direct sunlight to give HCl, and that reaction is explosive. So, you may remember studying this H2 plus Cl2 in diffused sunlight. You need to perform it in diffused sunlight. What happens when it is in direct sunlight? The speed of the reaction will be very high, so high that it ends up in an explosion. Yeah, so that's what we mean by radiation, presence of light. Okay, certain reactions are, the speed of certain reactions are changing or influenced by light. Okay, so out of this minimum 4 points you should study. Definitely you should study minimum 4 out of the 6. Now, so far we understood what is rate, what is average rate, what is instantaneous rate, and in a complex reaction, as in when the coefficient in front of all the reactant and product is not exactly equal to 1. Then how do we write the rate of the reaction? Then we studied the factors which influence the rate of the reaction. Now the question arises is, how do we find out the actual rate of a reaction? Is it only theoretical? Like so far, whatever I have explained to you is theoretical. You look at the equation and you predict the rate of the reaction, isn't it? Now, there is another way, another theoretical way of finding out the rate of the reaction. But one more question is arising here. Is this theoretical determination always true? Okay, let's find out answer for this question. So first of all, 11th grade, we have studied this law of mass action. Law of mass action is helping us to find out the rate of a reaction. Law of mass action is helping us to find out the rate of a reaction. According to law of mass action, okay, at a given temperature, the rate of a chemical reaction is directly proportional to the product of molar concentration of reactants with each term raised to the power of the respective stoichiometric coefficient, the number in front of it, as represented in the balanced equation. Look at this equation. Okay, this is little difficult to understand if you don't remember what you have studied last year. So let me explain this. This is the hypothetical reaction which I have taken. A moles of capital A. So capital A, capital B stands for certain chemical compounds. Small a and small b stands for the number of moles of that compounds. So according to law of mass action, rate of the reaction R is directly proportional to, let me cross check, see, directly proportional to. So now directly proportional to the product of, so I've just put a into mark here, product of molar concentration. So I'm putting square brackets to represent molar concentration of the reactants. What are the reactants? A and B, capital A and B. Each term raised to the power of respective stoichiometric coefficient. How many moles of A I had taken? A moles of A. And how many moles of B? B moles of B. So, this is what law of mass action. According to law of mass action, at a given temperature, rate R is proportional to product of into molar concentration of reactants A into B with each term raised to the power of stoichiometric coefficient A to the power of A into B to the power of B. Now I need to change the proportionality sign. So I'm introducing a constant. R is equal to K into A to the power of A into B to the power of B. A to the power of A into B to the power of B. Okay, so that is the representation of a rate of the reaction according to law of mass action. But what is this K here? K is called the rate constant of the reaction. K is called the rate constant. Okay, K is called the rate constant of the reaction. All right. Now, this expression is based on theoretical facts that we know. I have already told you this is a theoretical way of determining, finding out the rate of a reaction. Theoretical way of finding out the rate of a reaction. So that's what we mean by this is based on theoretical facts. Now, is it always true? That was our question, right? Let us check. Okay, so for getting an answer for is this true? Okay, I've taken a equation here. N2O5 decomposes to give NO2 plus O2. According to law of mass action, okay, according to law of mass action, this has to be the rate. R is equal to K into N2O5 to the power of 2. But experiments have proved that rate is equal to K into N2O5 to the power of 1. Why is it so? Meaning, first of all, we understood that the theoretical calculation of a rate of a reaction need not be true or may be true under certain given set of condition. So it becomes our responsibility now to check what are those set of conditions. Let's see. Here, this tells us about, that is rate law expression, tells us about the actual dependence of a rate of reaction on the concentration of various reacting species. So straight away they are telling here law of mass action need not be true, or it is not always true, or it is true only under certain conditions. So there is something more that we need to understand, like the rate law expression. Rate law expression tells us about actual dependence. Actually, what is the rate? Actually, how is the rate dependent on the concentration of the reactants? So, actual dependence of rate of reaction on the concentration of reacting species. It is based upon the experimental fact and is always written for the slowest step in the mechanism of the reaction. Okay, this will become clear in a while. So till then, let's leave it as it is. Okay, so an expression or the meaning of rate law expression is the experimentally determined relation between the rate of a reaction. Experimental relation between a rate of a reaction and concentration of reactants. That is called rate law expression. How is this different from law of mass action? Law of mass action was a theoretical determination. You will write the balanced equation, you will check what are the reactants, you will check how many moles of the reactants are written in the balanced reaction. Accordingly, you predict the rate of the reaction. Whereas in rate law expression, you will conduct experiments, and on the basis of experiment, you will develop a relation that connects the rate of the reaction with concentration of reactants. So this you must study if the question is, what do you understand by rate law expression? You can write this. Experimentally determined relationship between rate of a reaction and the concentration of reactants is called the rate law expression. Now we came back to the same equation. Okay, so as per LMA, law of mass action, this is supposed to be the rate, but actual experiments have proved R is K into N2O5 to the power of 1, though I have taken 2 moles of N2O5. Only 1 mole is affecting the rate of the reaction. So why is it so? Let's find out the reason. Reason is decomposition of N2O5, nitrogen pentoxide, takes place in 2 steps. Though we wrote the reaction in a single step, reaction is not as simple as we represented it. It is a 2-stepped process. In that 2 steps, first step is decomposition of 1 mole of N2O5. Out of the 2 moles, only 1 is decomposing. 1 mole of N2O5 decomposes and you are getting NO2 plus NO3. 1 mole of N2O5 decomposes. So after that, 1 NO2 plus 1 NO3 you are getting. And here I have mentioned it is the slow, or it is the slowest step of this reaction. Moving further, in the second step, that NO3, which is a product of the first step, NO3, which is a product of the first step, that combines with N2O5, the second mole of N2O5, right? We have taken 2 moles. So initially only 1 reacted. The second N2O5 reacted with NO3. NO3 is the product of the first step. And you will get 3NO2 plus O2. Your result is 3NO2. But this and O2. But this is a fast step. The net rate of the reaction, entire rate of the reaction is determined by the slowest step of the reaction. Slowest step of the reaction determines the speed of the net reaction. Now, apply law of mass action in the slow step. When you apply law of mass action in the slow step, then rate is K into concentration of N2O5. So we got an answer that law of mass action, you cannot generally tell that, oh no, it is not always holding good. Sometimes it is true, sometimes it is not. No, law of mass action is always correct, provided you find out the slowest step in a multi-stepped reaction. Whenever your reaction is complex meaning whenever your reaction has more than 1 step, then find out the slowest step. Apply law of mass action to the slowest step. And thus, you can find out the rate of a reaction. Okay, now you may be thinking that, so should we by heart all the steps involved in every reaction? How do we know which is taking place in 1 step, which is taking place in 2 steps? Yeah, we don't know, right? So, we will not by heart all this. Say N2O5 is giving a first step NO2 and NO3. Maybe this we have to study to understand, what exactly is the relation between law of mass action and rate law expression. One example is good to study, but we are not sitting and by hearting all such reactions. Such reactions, if it is a multi-step to one, the slowest step will be mentioned. It will be given to you. That this is the slowest step. So you just need to apply law of mass action to the slowest step. Okay. Now, order of a reaction. Order of a, this is another term that we need to study. Order of a reaction is defined as the total sum of the powers to which the concentration terms are raised in the rate law expression. Before taking this example, let me go back to the previous reaction. The overall reaction is this. 2N2O5 gives 4NO2 plus O2. But rate law expression, this is called the rate law expression. In the rate law expression, sum of powers to which the concentration term is raised, there is only one concentration term here. It is raised to 1. Right? So here the order of the reaction is 1. This is an example for a first order reaction whose order is 1. So sum of powers to which the concentration terms are raised in the rate law expression, sum of powers 1. Okay, in the rate law expression. So this is a first order reaction. Now let us look at this hypothetical reaction. I have taken A moles of A, B moles of B, C moles of C. They are reacting together to give us some product. Okay, according to law of mass action, let me write LMA. According to law of mass action, R should be K into A to the power of A into B to the power of B into C to the power of C. But now we have realized the rate law expression. That is the experimental one. R is equal to, rate is equal to K into A to the power of P, not A to the power of A. P need not be equal to A, but P can also be equal to A. So I hope you are understanding the difference. P can be same as A. P need not be same as A. So A to the power of P, B to the power of Q, C to the power of R. If you know, if you compare this with the previous example, you will understand this. According to law of mass action, the previous one was N2O5 to the power of 2. But according to rate law expression, R is K into N2O5 to the power of 1. So the, power as per LMA was 2, but power as per rate law expression is 1 in the decomposition of N2O5. Same way here, R is K into A to the power of, instead of A, we are writing P, B to the power of Q, C to the power of R, and order of the reaction is add the sums together. P plus Q plus R, P plus Q plus R. That is order of the reaction. Now, when we do some numericals, this concept will be more clear. Okay, so examples of different order reactions. 0, first, second order reaction. This is, if you can memorize, you are, strongly encouraged to memorize this. Chances are less, but yeah, if your target is 100, right, then you better study at least one example. 0 order reaction, decomposition of ammonia to form nitrogen and hydrogen. First order, the previous one you can study, that N2O5 one, or NH4NO2 decomposes to give N2 plus 2H2O. Second order reaction, 2NO2 gives you 2NO plus O2. Our focus mainly in this lesson is on a first order reaction. Okay, so in the next episode, I'll be coming with numericals, which will help us to understand what exactly order of a reaction is, and then we will be studying the unit of rate constant. Okay, so please stay tuned for the next episode. Thank you.